welcome everybody to today's webinar. My name's Dan Combest, and today my colleague Paolo Geremia out of our office in Italy is going to be presenting a topic on open source CFD solutions for the marine industry. Some of the webinar goals. Today we'd like to demonstrate ENGYS innovations for the marine industry, show some of the verification and validation efforts here at ENGYS, and demonstrate how to set up a few cases in HELYX specific to this particular industry. In terms of questions, we'll answer all the questions at the very end, and we can continue via email post-webinar. So if you have your meeting invite to this, if you hit reply, you can ask a question directly through that. Just a little bit of information about ENGYS as a company. We are global providers of CFD software products and services. Originally, we were founded in the United Kingdom in 2009, so we're celebrating finishing our 10th year of business. We've always been focused on enabling open source software in industry, specifically foam and open foam developers since 1999. We have a lot of experience within our company with that library. We have 7 offices worldwide: the UK, Germany, Italy, here in the US, Australia, South Africa, and Brazil. And we also have an established distributor network around the world in Japan, South Korea, here in the US, France, and Spain. In terms of the products that we offer, HELYX, which is a general purpose open source CFD software suite. We also have Elements, which I'd consider a superset of HELYX, and this one's aimed more towards CFD in the automotive industry. So there's external aero best practices, additional tools for thermal underhood management. Another group would be HELYX add-ons, adjoint optimization tools. If you've been attending some of the webinars that we've had several on adjoint optimization. We also have a block coupled solver add-on. We also have a marine hydrodynamic solver, which is what Paolo will be talking a little bit about today. And then also some add-ons related to advanced multiphase flow. And then finally, we have HELYX OS, which is an open source graphical user interface for standard open foam that you can download for free on Linux. And you'll find that on our company website. So today's topic is open source CFD solutions for the marine industry.
Thank you, Dan, for the introduction. Today, I'm going to talk about HELYX Marine, an open source CFD tool for naval architecture and marine industry. And in this presentation and in this demonstration, I will walk you through the different components of the software itself, ranging from calm water resistance methodology that we have implemented in HELYX Marine, then talking about seakeeping, propulsion modeling and self-propulsion in particular, maneuvering, cavitation, hydroacoustics, and then a few words on current developments. Let's talk about HELYX Marine. Well, HELYX Marine is an add-on of our HELYX open source software, which is designed for naval and marine application, and it consists of different components, starting from a single-phase linearized free surface solver, which is an hybrid runs and free surface solver, which is designed for several applications, starting from calm water resistance, maneuvering, self-propulsion, and transient and simulations. So you can run both steady state and transient. We will see later on how it works. And this is an approximate method. Then we have a high fidelity method, which basically consists of a 2-phase volume of fluid VOF solver, which also supports dynamic mesh motion, which is designed for calm water resistance, seakeeping, self-propulsion, and maneuvering. And as such, it's basically our preferred solution in case of high and accurate solution that we want to achieve. Then we have different tools for propulsion modeling. cavitation, and hydroacoustics. And I will touch on those later on during this presentation. In terms of contribution, the solver technology has been developed in collaboration with the University of Michigan in the US under the supervision of Professor Kevin Mackey from the Department of Naval Architecture and Marine Engineering, whereas all the implementation, testing, validation, maintenance, and software development is done by ENGYS. Talking about calm water resistance, we have different methods, like I said before. Let's start from the first one, the linearized free surface solver. Why we have this tool? Well, traditional methods are based on fully viscous run solver like VOF, which is a well-established method in naval ship hydrodynamics. But for certain cases, for certain range of application, we want to have something quick and fast to run to have a quick assessment of the performance of the hull. So if you want to do things like hull form optimization, you need to run things like DOE, parametric studies, and so on, and you need to explore your design space as quick as possible, and you need to have something reliable that can give you the correct trend in terms of performance and the results. And this is why we designed this solver, which is basically an hybrid method between a traditional runs methodology with a combination of a free surface effect. So it actually models one side of the domain, just the water side, and applies a linearized free surface boundary condition on the top. And as such, it can compute both the hull resistance and also approximate a sinkage and trim. Because of its internal formulation, it runs up to 100 times faster than traditional VOF methods. The range of application is basically limited to low fruit numbers, so low speeds, and slender body hulls. It can run both steady state and transient, like I mentioned before. And looking at validation, there are several tests that we've been running across the latest 10 years. And this is one of the initial tests that we ran, and you can find a reference down here. So this is the Gothenburg 2010 workshop, case 31B. So this is the US Navy combatant DTMB 5415 hull form. And on the left side here, you can see the results of the CFD versus the experiments for a specific fruit number, a specific speed, and you can see the correlation with the experiments. On the right side, instead, we have a full resistance curve at different speeds. So in black, you have the experimental results, and the different colors show the results of the resistance coefficient at different grid densities, basically, in case you want also to look at the grid convergence study. But coming back to the benefits of this solver with respect to the traditional methods, well, if you want to perform ship hull optimization, like in this case, which was done for Fincantieri, an Italian shipbuilding company, so say we wanted to optimize the hull form for 3 different speeds at 0.15, 25, and 30, a full number, while keeping the displacement constant. Well, what we did was to take the baseline shape here of the hull and do morphing of the bulbous bow shape. Unfortunately, I have only one view here, which I'm allowed to show, the side view. But we fed this into an optimization loop to run multiple alternative solutions and different design solutions to get the optimized shape you can see here on the gray. So the transparent shows the baseline, and the gray one, the optimized one. And looking at the results, on the top here, we have the flow pattern for the wave pattern for the baseline, whereas the optimize looks like the one underneath here. You can see there's a different wave elevation pattern on the floor section here of the hull. Looking at the quantitative results, displacement was pretty much the same, so was fixed. And in terms of total resistance, we notice things got worse at low speed, but higher speed we got 6% improvement. And since the client was more interested at higher speeds, we gave more importance to this speed. So results were validated against a VOF solver and were actually confirmed. So the trend is actually captured quite well with this application for certain kind of hull forms, like I said. In case you want to look at, you are more interested at the accuracy of the results rather than exploring the design space, like I mentioned before, well, you have to go for the VOF solver, which is a two-phase flow solver, which accounts for both the air side and the water side, and is very accurate for calm water resistance. It also includes 6 DOF body motion. And in terms of ship motion, you can have different outputs, like, for example, sinkage and trim. In terms of application area, well, it runs fine for both displacement and planing hulls at all through the numbers. Similar to the linearized free surface solver, also for this case, we have a series of validation test cases that are available from literature from different workshops for the marine community, and I just pick up one here which is relevant to this solver. So, for example, here we have the Criso container ship, the KCS from the South Korea Research Center. And this is the again the Gotemur 2010 workshop. We have a fixed speed 0.26 scale model and fixed position and even keel, and the mesh is basically 2.1 million cells for this particular case, including near wall extrusion layers. Looking at the results for case 2.1, we have the wave elevation, so the wave pattern here. On the top, we have a CFD, and on the bottom, we have the experiments. And you can see here there is a good agreement in terms of wave profile. And if you look at the wave cuts and wave profile on the hull, for example, on the top left here, this is in blue, we have a CFD, in red, we have the experiments. There's a good correlation with the experimental measure with 2.1 million cells, which is a medium-sized mesh, which was considered for this study. And then we have different wave cuts on the side of the hull at different distances, so moving away from the hull to the far field. Basically, we have different cuts, and you can see how the CFD results match the experimental results. Of course, similar to the linear free surface solver, even for that, you have to go through the grid convergence studies to do mesh sensitivities. So this is all part of the validation process, but it's not mentioned here. If you want to consider the full resistance curve, so see how the hull respond at different speeds, you take the same computational grid and you just run at different speed by keeping the exact same settings, and this is what you get. And you can see how the wave pattern changes moving from low speed to high speed. So you can see here that the number of wave feature has been increased with respect to the low speed, as expected, of course. In terms of numerical results and quantitative results, this is the total resistance curve for the different speeds. And you can see in blue the experiments, in red the CFD. Then this is again using a specific grid which was kept fixed during the resistance, the total resistance curve study. If you want to account for sinkage and trim, so you run with 2 degrees of freedom, heave and pitch respectively, this is what you get. So these are the numbers for sinkage, and again in blue we have the experiments, and in red we have a CFD, and for trim this is what we get. So there's again a good correlation with the experiments for this particular hull form. Before we move to the next topic, which is about seakeeping, let's have a look at our graphical user interface to see how you can set up and run a specific case to perform calm water resistance. So let me switch to this. So first of all, when you open our graphical user interface, you have to create a new case. So say we want to predict the calm water resistance at a specific speed for the DTMB 5415 model, which I showed before as a validation case for the linearized free surface solver. Let's say DTMB here, and then 5415. We run on 4 processors. You just select a parent folder where you want your case to be saved, and you just click OK. First thing to do is to import the geometry from file in this particular case. So we have a HAL file which is saved in STL formats. We have different import format options, including STL, OBJs, IGES, and STEP. So we select STL. We click Open, and this is how the HAL form looks like. So we just model half of the domain here. And let's start with the linearized free surface solver. For that, we have specific best practices and configuration file in order to create the background mesh, which is probably the most critical part for this simulation study. So having a good mesh is key to get good results for any ship hydrodynamic solver. And for this particular case, we have defined a specific block mesh, okay, which is fully parametric and is based, as I mentioned before, on our configuration files based on our best practices, and it accounts for things like the length, the width, the height, and the center of gravity, and other operating parameters. And based on that, it will create the computational mesh. For the hull, we need to define the refinement level, so say 1 and 2, and we need to define the surface boundary refinements, the surface, the snapping surface boundary, in order to get accurate resolution on the boundary themselves, and then define the near wall layers here. For example, we put 5 layers. And once you're done, you hit Create Mesh. I already have this case run for you just to speed up things. So this is how the computational mesh looks like. For this particular case, we are talking about 900,000 cells, 931 basically. And so you can see, as mentioned earlier, we are only modeling the water side. So let me show you here, just to give you an idea about the layer coverage. This is the apt section. If you look at the 4th section here, it's a bit tricky because you have to refine a little bit further on the sonar, on the bulbous bow here, and you can see how it looks like. So this is the side view. If you go and look at the top view, this is what you get. Again, this is the near wall layers on the free surface. And as you can see, there is some stretching applied here on the cells in order, when you move away from the hull, in order to optimize the cell count. looking at the result, this is what you get. So if I show you here, this is the free surface, water elevation. This is the contour you get, okay, after, in this particular case, 6,000 iterations. And how do we do this? Well, once you get a mesh, like in this particular case, you go to the setup and you select the solver. We have different options. We have segregated couple solvers, and then for this particular case, we run steady state and incompressible flow, and we select marine here. You have to specify gravity as the direction of the gravity vector, which is negative z in this particular case. And then you move to the material section where you prescribe the material properties for water in this case, so basically density and viscosity, since you're running incompressible. In terms of turbulence modeling, we run runs for the water side and k omega SST as turbulence model, which is one of our standard validated turbulence model for calm water resistance prediction, and it works pretty well for a wide range of cases. Moving to the next station, which is called free surface. This is where you prescribe the settings for the linearized free surface boundary conditions. So you have to define the free stream velocity here, and the numerical bits where you basically apply some dampening to the domain. This is a sort of a ring which is placed inside the domain with a specific distance and width, and a series of patches and surfaces where it's computed from, and then a series of parameters like such as relaxation factors. In terms of boundary condition, we have, for example, here a list of patches. So we have bottom, inlet, and side, which are highlighted here in red. And for this, we just apply the far field, the free stream velocity, basically to the 2.097 meters per second. Same for turbulence. We have fixed values here. Okay, same for bottom. On the top, as I said, we have a free surface, special boundary condition. Then, since we are modeling just half the domain, we use a symmetry plane on the central of the central plane, whereas on the hull we use a stationary wall. And finally, we have an outlet, a pressure outlet on the other side. In terms of numerics, we run second order for both gradient and advection schemes. As I said, we have developed best practice for basically any solver available in HELYX, and also this also includes our marine software tools. Then we have solver settings. We just use relaxation factors for the equations. We run for 6,000, and we want to monitor the forces on the hull. Okay, in terms of forces on X, Y, and Z direction, and also moments. And before we run the solver, we just initialize using one of the available methods. We just use a fixed value to keep it simple here. Since the problem is quite simple to solve, we use a fixed value, the same values we have at the inlet for the internal field. Once we are done with that, we just hit initialize, and then you run the solver. And this is what you get, basically. So these are the forces. And if I show you the resistance force on the X direction, you can see here that it converges to a steady state value, since we are running steady state here. So this solver can be applied in different ways, and in this particular case, this is the kind of behavior you get out of this. If you want to solve the same problem using a more accurate method using for example, the VUF solver which I mentioned earlier during the presentation. This is what you get. I'm loading the case here. Okay, so you see here you're modeling both the water and the air side. And if we look at the mesh, this is how it looks like. So you can see we are refining around the hull block and using very high aspect ratio cells on the free surface in order to, I mean, these are kind of squeeze cells to, you know, save cell count and also have an accurate resolution of the wave pattern on the free surface, also on the far field, you see here. And looking at from the top view, if I look at the top, this is a cross section of the mesh on the water line. This is what you get. So since we are dealing with calm water resistance, you need to refine around the hull and make sure you get all the waves right. So we are using anisotropic refinement boxes that we have available and implemented in HELYX, and this allows you to get very accurate results in terms of flow resistance and wave pattern. If we look at the final results here, for this particular case, we are running a transient version of a VF solver with large time steps. We can also run steady state if you want. And looking at the phase fraction, so if I show the phase fraction here, you can see the wave pattern on the hull, and looking at the free surface elevation, this is what you get. Okay, so these are the contours. If we look at the forces, the resistance force, for example, like we showed before for the linearized free surface solver, this is what will be shown by the GUI. So just showing the X component here, and then you can see here there's a transient and then behavior which is dampening and converging to a constant value, as you might expect. Okay, so that is the two worked example, two hands-on tutorial cases how to run this calm water resistant with HELYX for a very simple case. So we just try to solve the DTNB 5415 with no mesh motion, and we're just looking at the wave pattern here and the flow at the resistance value. Moving to Seakeeping, well, we have two different options available in the solver, which is the VUF solver, and two different rigid body motion. One which runs in 5 degrees of freedom, where we have a surge which is enforced, just to mimic what happens to inside the towing tank. And this is when you want to do Seakeeping and other resistance studies. Then we have a full 6-off option to model floating objects, buoys, you know, floating structures for offshores and so on. Since we are dealing with Seakeeping and other resistance, we have a wave generation library for both regular and irregular waves. And looking at validation cases, one which I've selected here for today is the Tokyo 2015 workshop. We have 5 different cases of wave conditions, and this is again a model scale for which we have experimental measurement available from the workshop website with mass and inertial properties and all the different geometry and conditions provided. In terms of wave condition, we move from C1 to C5, from the shortest wavelength to the longest wavelength. And in this particular case, the objective of the work was to calculate the resistance coefficient, heave, and pitch time history motions by taking the raw data signal and then reconstructing using a Fourier transform and compare to the experiments. For this purpose, we use a 2 degrees of freedom version of a solver. So we allow pitch and heave motions, and showing just the C1 and C5, so the shortest wavelength. Here, the C1, you can see here the wavelength, the wave elevation now, and how this compare to the hull length. So we have resistance in blue, we have CFD, in red we have the experiments, then in the bottom we have heave and pitch motions, and you can see there is a good correlation with the experimental measurements. Moving to the longest wavelength, you can see here that the wavelength is comparable to the length of a ship, so it's very tricky case here, and you can see the response of the system in terms of resistance, heave, and pitch motion for this Seakeeping simulation study. Okay, that was the Seakeeping side. Then moving to propulsion. We have different models for self-propulsion, starting from discretized propeller models, which are used for simulating the ship operating point in self-propulsion conditions. So you can either choose a fixed RPM for the propeller or a variable RPM, which is which basically employs a PID control system to change the RPM based on some target function. So, for example, you can either fix the RPM itself, or you can measure you can apply the towing tank force for the skin friction correction, for example. And this requires, of course, like as you can see here in this animation, a fully transient moving mesh. So not only the hull, but also the propeller in relative motion. In addition to this, we also have actuator disc models for the propeller. So we replace the discretized propeller with actuator discs using a body force model. And looking at the validation test cases for this, we have again one test case taken from the Gothenburg 2010 workshop. This is the KCS hull form, case 2.3a, and we have different condition. The one I'm showing here is the one with variable RPM, and you can see here the results in terms of axial velocity. So on the left, we have the axial velocity contours downstream the propeller plane at a specific distance. And on the right side, we have the CFD results. So in this particular case, we are showing just the instantaneous velocity values on the measurement plane. Looking at the velocity components in X, Y, and Z, so we have U, V, and W components respectively. This is what you get on the measurement plane downstream the propeller plane. And you can see here how the results correlate with the experiment. Okay, if you want to save time, and if you want to run a little bit quicker, you might want to go for an actuator disc model, a body force model. So you replace the propeller, the discretized propeller, with an actuator disc, which actually applies a body force momentum source. And there are different options. So either you provide a user supplied constant thrust and torque, which is spatially distributed, like you can see here on the bottom. Or you can also define time varying torque and thrust curves as a function of the advanced coefficient J. And as such, the body force model will apply the correct thrust and torque based on the operating point. We are working on other models that I'm going to show you later on the latest part for maneuvering, but this is basically the most validated one that we have available. Of course, in addition to the sail propulsion models, we do also run open water tests. So we can employ either steady state, static mesh, using MRF, so we can run the full 36-degree span of the propeller, like in this particular case, or we can run just a model sector. We just take one blade and we use MRF to save computational time. This is steady state. Also, we run transient with moving mesh, with sliding mesh approach usually, and this is done to calculate the characteristics of a propeller and get validated results compared to the experiments in terms of thrust, torque, and efficiency. Of course, even for that, we have a range of validation cases. You always start from the post-arm propeller as a start, and we have a list of validation cases available, which we collected across the years. But in this particular case, I just want to show you the results of a blind test we ran for roll propellers, which is an engineering company which develops and manufactures high efficiency propellers. So the idea was to get the geometry from the client here and perform a blind study to evaluate the HELYX accuracy using a full propeller model and also just one sector model for one blade to compare against the experiments. And this is what you get. So in terms of results which were provided by the client a posteriori after the results were delivered to the clients. And we have best practices available for this kind of modeling. Moving to the maneuvering side, we have different models available for carrying out captive maneuvering tests. So we have a library for running a planar motion mechanism using both the linearized free surface solver running in transient mode. This is an unsteady runs solver, which I showed before. Or if you want to run with a high fidelity valve, you can do it as well. In terms of tests you can perform, you can do static drift, like in this particular case, or pure sway or per yaw. Let me show you, for example, validation results using the linearized free surface solver, which is the low fidelity model that we have available in HELYX Marine. And here we can run with very large time steps this transient solution, this transient problem for running pure sway. So this is taken from the Seaman 2014 workshop, test ID 176. We prescribed a specific sway amplitude and a specific period. And this is what you get in terms of results for the sway force here on the left and the yaw moment on the right. So black is CFD and red is experiments. You can see here the correlation with experiments. On the right, we have an animation of the free surface elevation as a function of time. Looking at the pure yaw, you can see how the motion looks like in terms of wave pattern here and the correlation with experiments in terms of sway force and yaw moment. Cavitation modeling is also available in HELYX Marine. So what I would like to show you today is one test cases, one of our test cases that are available, publicly available. This is the ISQ propeller from the NMRI Japanese institute, and this propeller was made by Nakashima Propeller in Japan. You can find the link if you are interested in downloading the the geometry model. We employed the Schneider-Sauer cavitation model available in HELYX Marine, and we ran for a specific cavitation number with non-uniform inlet condition. In actual way, let me show you what I mean by this. So you just basically model the propeller in open water condition, but considering the effect of a propeller mounted, behind the hull. So you operate in non-uniform conditions, inlet conditions here. And this is quite tricky. You can solve the problem both using, steady state approach or, an MRF transient approach, but also a fully transient dynamic mesh motion, which was used for this particular case, because the idea was to, calculate, of course, the characteristic of the propeller in terms of thrust and torque as a function of time, but also to look at the pressure fluctuation as a function of time. So we have to go to run fully transient anyway. So if you can see here, you can see the characteristic of the propeller, the thrust and the torque. You can see the this periodic function, the behavior for the two curves, and the same for the pressure measured on a specific probe location point. And this is a reconstructed signal. So you take basically the harmonics of a Fourier transform, and you just use that for visualizing the filter data. In terms of a cavitation pattern, this is how it looks like. So this is the suction in the pressure side, and you can see here the effect of the non-uniform axial wake is clearly visible also in the size and the shape of the cavitation pattern. Okay, let me move to the next one. So acoustics. Well, we have a series of tools available for hydroacoustics. And so from low fidelity to high fidelity models. Before I show you these, one thing which is mandatory to get good results is, of course, to have a good solver in terms of calculating the correct pressure signals, and things like calculating pressure pulses on the hull is of key importance. So this is what we have here. Is the PPTC 15 workshop validation test case. So this is a propeller mounted on on an inclined shaft. This is a 12 degrees inclination angle, and you can see here the propeller from the top, and we have a wall just very close to the propeller blades and 3 measurement points. It's fully wetted propeller, and these are basically the animation showing the pressure as a function of time. You can see the pulses here, the pressure fluctuation on the surface. Looking at the pressure signal on the 3 measurement points, this is what you get in terms of raw data. We do have all the experimental measurements available, and the idea was to take the first 3 harmonics for the 3 different signals measured on the 3 different locations and compare to the experiments. And this is what you get. This is running fully runs. You can run this with more advanced methods like DES and LES if you want to account for more the effect of turbulence, for example, on the propeller tip, the tip vortex and things like that. But in this case, we are just focusing on runs to keep it simple. And then once we get a good correlation with the solver itself for the source part, we focus on the propagation part. So in this particular case, we use the Fox-William-Hawkins propagation methods, the line of sight method. And we just show here the results of a simple validation case. We just take the propeller from the KCL's hull form, and we measure the acoustic and runs pressure on the 3 points very close to the blades, and they should be very correlated each other. So, and this is what you get also using our approach here, our method basically. And you can see the curve for P1, P2, P3, which are the 3 measurement location on the hydrophones, and we have in black we have the the acoustic pressure, and in red we have the hydrodynamic pressure. This is on the time domain. If you move to the frequency domain, this is what you get. So there's good correlation also of the main harmonics and peaks. Of course, you can expand this and run with a different turbulence method and more accurate and grids and so on, and get even better results. If you want to make a step further and look at things like underwater noise, this is what you have. In this particular case, we have, you know, the KCS half form, and we run in model scale a specific speed, and we measure the sound pressure level in different location in deep water condition. And this is you can see here the pressure pulses on the hull, and here the sound pressure level on the hydrophones at a specific depth. In terms of developments, we are focusing on maneuvering, free running tests. More specifically, we have a paper which has been submitted to the Seaman 2020 workshop, and this slide shows you the comparison with the experiments about the Zigzag 2020 test case of the KCS, you know, used for the Seaman website workshop. So in this particular case, we are running a specific speed, model scale, and we compare the experiments in terms of heading and rudder angle between the CFD and the experiments. And this is on the left, and on the right we have a rudder rate, CFD, and the experiments. And whereas on the right you can see here the free surface elevation on the top, and on the bottom we have the velocity measured on the free surface. This is using the linearized free surface solver. Of course, we can run this using the VF solver, but using the for this case, we use the linearized free surface solver just to run with larger time steps and faster. This kind of simulation are very demanding in terms of computational time. And finally, we employed a brand new propeller model based on a response surface methodology. So we have a training set of different conditions for the creation of the, this regression model for the propeller itself. So it's kind of non-conventional propeller model. In conclusion, HELYX Marine is a high quality tool for marine engineering. Is fully open source. It's being developed since 1999 by experts in open source technologies, developing foam and open foam. We provide a good quality support for our customer in order to make sure they use our software in production. We keep assisting them, of course. It runs both Linux and Windows. It's fully validated and customizable since it's open source, and scalable. There are no extra costs for HPC, and it's cloud ready since it's provided. It comes with a fully native client server framework.